Welcome to the Heap Feng Shui talk. This is the future of exploitation, so I hope you won't be disappointed. So what is Heap Feng Shui? Besides just being a cool title for a presentation, it is also the art of arranging heap blocks to make exploitation easier, to ensure that when you overwrite data on the heap, you're overwriting the exact block that the exploit author intended. It is not a new technique, but the implementation that I'm going to present makes it very, very easy to implement things like this in Internet Explorer. I'm going to talk about these heap manipulation techniques implemented in JavaScript, which makes it very easy to exploit a variety of browsers. The actual implementation that I'm going to demonstrate, and it should also be on the CD, is supports Internet Explorer 6, I think 5, 6, and 7. But certainly these techniques can be applied to pretty much any system that supports JavaScript or a similar execution environment. In fact, we have seen some more sophisticated exploits that are using similar techniques even without any client-side scripting. So I will talk about those briefly in a little bit. So this talk is going to have a couple of parts. First, we're going to start with, is this echo normal? Or? Okay. So first we'll start with what the state of the art in browser exploitation is. I will cover a couple of exploits that have come out over the last year and the techniques that they used. I will talk about the traditional stack and heap exploitation methods and why they no longer work or work in very limited circumstances. Then I will talk about, I will present the heap manipulation. Higher? Is this better now? Okay. So we'll start with the state of the art. Then I will introduce the Heap Feng Shui idea, which allows for these precise manipulation of the heap. And I will show how to implement it using Internet Explorer. In order to do this, I'll have to cover the Internet Explorer heap internals. I'll show how the different pieces and components of Internet Explorer allocate memory and how we can utilize these components to get our blocks to be in the right places. Then I will demonstrate the so-called heaplib JavaScript library, which is a very user-friendly, object-oriented JavaScript library that you can import into your exploit, and it provides you with a variety of functions that are very useful for heap exploitation. The source code of the library should also be on the CD. It is BSD licensed, so you can use it pretty much any way you want. Finally, I will talk about, I will give specific examples of the heap manipulations that are possible using this library. I will show one of the exploits that I developed using the library. I will walk through it and demonstrate how it works. And then I will talk briefly about the potential mitigations for preventing techniques like this from working in the future. None of the mitigations are very good, though, so if somebody wants to work on a cool project, maybe they can figure out a better way to stop this. I personally prefer working more on the attack side than the defense side. So let's start with the browser exploits that we've seen recently. The generic exploitation techniques that have served us very well for a number of years no longer work very well, or work in very limited circumstances. Probably the most common and standard exploitation technique is the buffer overflow on the stack, where you override the return address. and redirect the program execution to your shell code. This is pretty much mitigated by the GS flag in the Visual C++ compiler. In almost all cases, it prevents the exploitation of return address overrides. There are some exceptions to that. There have been cases where a function was not protected by GS, even though it should have been. The ANI exploit in the beginning of this year was one of those examples, but this is a pretty rare occurrence. So you can pretty much count that your standard vanilla buffer overflow on the stack can no longer be exploited just by overriding the return address directly. The other thing that you can override on the stack are the SEH frames. By overriding these and causing an unhandled exception, you can get shellcode execution because your shellcode will appear to be registered as an exception handler. The SEH frames are also stored on the stack. They're right before the return address. So they're pretty convenient. They're a pretty convenient exploitation method, but they also don't work very well in 2007, mostly because of the safe SEH feature in the recent versions of Windows. If your code was compiled with the safe SEH flag, all the exception handlers in the program will be registered in a special table inside the binary. And if you try to execute an exception handler that is not in that table, the operating system will just refuse to jump there. And obviously, your shell code will not be registered as a valid exception handler. And since this exception handler table is in the actual binary and it's in a non-writable segment, you can't really do much with it. So if your binary is compiled with this option, then SEH overrides are also, in almost all cases, not exploitable. Finally, the last thing you can do with a stack-based buffer overflow is you cannot override the return address because of the GS protection. You cannot override the SEH frame because of the safe SEH. What you can override are the local variables that are stored on the stack frame before the SEH frame in the return address. Overriding those also no longer works because the latest versions of Visual C++ reorders the local variables so that your stack buffer, where your buffer overflow most likely is located, will be at the end of the stack frame. So there will be no pointers or any other important pieces of data after it. So you will not be able to override them. In addition to that, the compiler will move the arguments of the function, which could also be pointers. It will move them to the top of the frame. So you can no longer override those either. So pretty much this makes the standard case of buffer overflows on the stack non-exploitable. So what does this leave us with? Heap overflows. Unfortunately, the generic heap exploitation methods for heap overflows have also been getting harder and harder to implement. Probably the most standard method is using the doubly linked list of free chunks, which is a list that links all the free chunks on the heap. In the past, you could use the unlink operation from this doubly linked list to override an arbitrary 4-byte location in the program. Unfortunately, in XP Service Pack 2, in 2003 in Vista, you can no longer do this because the heap allocator verifies the integrity of the doubly linked list. This was a very cool exploitation technique because it was completely generic. It didn't matter what application you were in, as long as it used the standard Windows allocator. You could just override the doubly linked list and it would work. Unfortunately, you can no longer do that. On top of that, in XP Service Pack 2, there is an 8-bit cookie in the header of each chunk. And before most operations performed by the heap allocator, the cookie will be checked. And if it doesn't contain the correct value, the heap allocator will bail out. So this means that you're no longer able to overwrite override the header. And on Vista, this has been improved by actually XORing the entire header, which serves to completely make it impossible to override a header with data that will appear valid because you do not know what the XOR key is. And finally, one of the attacks, I believe Matt Conover first found this, if I'm not mistaken. The look-aside linked list, which was a single linked list data structure used by the heap allocator, could be used to do a 4-byte, no, not a 4-byte, all right. It could be used to do heap exploitation in a mostly generic way as well. But in Vista, the look-aside has been removed completely and is now replaced by the low fragmentation heap, which is much more secure and doesn't have data structures like that. So what this means for us is that we cannot exploit generic heap overflows by attacking the heap allocator, because the heap allocator has been hardened to a level where, in the generic case, there is nothing that you can do with it. So what's left? I mean, does this mean that there are going to be no exploits for Vista, for example? Well, obviously not, since we've seen some already. The ANI exploit, which was one of the first vulnerabilities in Vista, was a very interesting case because it was in a function that was not protected by GS, and it still contained a stack overflow. The compiler doesn't insert the GS protection for all functions because of the performance impact. It uses a heuristic to detect which functions have buffers that are likely to be overwritten. Unfortunately for Microsoft, in the ANI case, the data structure that was being overwritten on the stack was not an array, so the compiler heuristic did not insert the GS protection. And you could exploit the stack overflow like it was back in 1999. There was no protection to bypass it all. Unfortunately, this is a very rare case, and I doubt that we will see a large number of these vulnerabilities. The other avenue that's still open for attack is the use of uninitialized variables. And by uninitialized variables here, I mean not only variables that have never been written to, but also variables that might have been initialized, but the data there becomes invalid and is used afterwards. For example, a use after free vulnerability I would consider an uninitialized variable bug, because you have a free block that some you have a block on the heap that some pointer points to, and after this block is freed, the pointer becomes invalid. But if the program still uses it, it will access the data that was just freed. And in the meantime, this data could have been overwritten, it could have some different contents, it could actually be completely unmapped, so maybe it's not even valid memory. Halvar Flake did some pretty cool work on exploiting uninitialized stack variables. His work was mostly focused on how to use static analysis to figure out which functions had overlapping stack frames. So you could use different code paths to initialize the uninitialized data, and then use another function, and then call another function that used this data, and now you control the values in it. Unfortunately, a lot of these